everyone, and welcome to the Joy of Abstraction Book Club, Chapter 22 on Natural Transformations. As you can see, I'm outside today because it's a beautiful day and it's perhaps one of the last really beautiful days in Chicago. So I decided I would try making this video outside to make the most of this beautiful day. I hope there's not too much background noise. You might hear a little bit of the L, a little bit of the road, a little bit of other people's loud music going past, but perhaps this will give us some atmosphere and make things seem a little bit festive as we approach the end of the book. It's so amazing. I can't believe how far we've got. I mean, I can believe it, but I'm just very excited about it. So here we are. We've got great questions about natural transformations this week, and I will jump right in. First question. You've talked a little about some things holding up to isomorphism, and I'm wondering if you could say a bit more about what it means for a property or something to hold only up to isomorphism. How is this notion related to something being on the nose? Well, this is a very important concept in category theory because it's practically the entire point of category theory, actually, because isomorphism is what we are using as a concept of sameness for objects in a category. So when we say that something holds up to isomorphism, what we're saying is that where there might otherwise have been an equality, we're putting an isomorphism instead. And that can hold in various contexts. The most common ones, and probably the ones that we have seen the most, are uniqueness up to isomorphism. So if you think about what uniqueness really means, it means that given any two such things, they are equal. And although that might not be how we usually think of uniqueness before we do category theory, because uniqueness means there is only one. But there is only one means if there is another one, it must be equal to that first one. So uniqueness up to isomorphism instead means that if there is another one, it's isomorphic to that first one. So other things only holding up to isomorphism tend to be equations. So things like associativity holding up to isomorphism. Well, what does that mean? Associativity is usually an equation saying something equals something else. So if it only holds up to isomorphism, that means that that equality is actually an isomorphism now. So those are, I think, probably the two most usual situations where something can be up to isomorphism, but really anywhere where there could have been an equal sign, or you could somehow interpret it as having an equal sign, is somewhere that we can now have up to isomorphism. So another one that we've seen is where when I talked about full and faithful functors, we were talking about surjectivity up to isomorphism, and we don't usually call it that when we're really doing category theory, but I called it that to explain what it is, because surjectivity in the normal definition, the usual definition, does have an equality in it, because a function is surjective. A function from A to B is surjective if for every object in B, there's an object in A such that f of A equals B. So where that equals sign is, then to make it up to isomorphism, we instead put an isomorphism. So if we say something is on the nose, then what we're saying is that actually that isomorphism is an equality. And we would usually only stress that something is on the nose if there was even the possibility of it being up to isomorphism instead. So if we were just talking about functions between sets, there isn't a concept of up to isomorphism for, say, surjectivity of a function between sets. So we wouldn't call it surjective on the nose because that emphasis would be redundant. But if we were talking about functors between categories, and if a functor turned out to be surjective on the nose, that would mean it's not even just essentially surjective, it's really actually surjective. Every single object gets hit, not up to isomorphism, but actually hit. And so then we would stress that it's on the nose because it's stricter than we might otherwise demand. Okay, that's that question. Next question. How do you pronounce the double arrow? I've enjoyed all of the questions about how you pronounce things, and I'm not sure if it's the same person asking those questions throughout, but it sounds like it's the same person, and it's really great. I'm glad that you're asking that, because it's good for me to be reminded that you need to have a way to think about these things in your head. So when you have F goes to G by a double arrow, we would usually say, what I would usually say, well, I should probably, how about I get the whiteboard up so I can show what I mean. Right. So if I were going to say, oops, I need a pen. If I were going to say, let alpha be a natural transformation from F to G, I would just say from F to G. Just like if I said F was a function from A to B, people do sometimes say A arrows B. You could say F arrows G here without specifying, but I would just say let alpha be a natural transformation from F to G. Good, next question. Within a category, objects are zero-dimensional and morphisms are one-dimensional, right? Yes, but then when we zoom out, categories are zero-dimensional and functors are one-dimensional, but where are we when we're speaking of this hierarchy? Is it in a category of categories? Yes. And so the point is that in a category of categories, the categories become the objects of that category. So in a category, the zero-dimensional things are objects, and the one-dimensional things are morphisms. In any particular category, you therefore have zero-dimensional things and one-dimensional things. So in a category of categories, say cat, the zero-dimensional things are the objects of this category, which are categories. Say small. Smell categories. Small categories, and the one-dimensional things are the morphisms between them inside that category. So those are probably functors. Okay, next question. Could you keep going up dimensions by using the quintessential arrow category in time interval type construction? That's a really interesting question. So when you use that interval construction to make homotopies in topology, the thing that's really clever about it, one thing that's really clever about it, is that you can get all dimensions out. In topology, we can go, we can start with a continuous map from X to Y, and that's the one-dimensional thing. And then the two-dimensional thing is a homotopy, which you can express as, let me see how I expressed it in the book, I cross X to Y. And then the three-dimensional thing is you can keep going like that, cross I, cross X to Y. And then the four-dimensional thing is I, cross I, cross I, cross X to Y. And one of the thing about it is that this I is a unit interval. And then here, what we have is I cross I, which is a unit square. And then I cross I is a unit cube, all filled in. Whereas in categories, if we take I to be the quintessential arrow category, and actually someone asked about this and asked whether 0 and 1 are the terminal and initial object. And the thing is that they're just labels in this category, but they happen to be the initial object and terminal object in this category as well. So the thing is that if you do I cross I, what you get is a square and it commutes. That means that this outside edge equals that outside edge. And so it's kind of not really a square. In a way, it's just a flat line. And so you don't get to build up any dimensions by doing that. It's just a line. It's kind of, it's a fake square because we don't have any isomorphisms. Oh, well, there's a loud plane flying overhead. Whereas in topology, I cross I sort of gives you another dimension because it's filled in. So the reason that we can't really do this in categories is that we just don't have any more dimensions in a category. If we were in a two category, then we could take a version of the I cross I thing with an isomorphism inside it. And that would be more like what this square is in homotopy theory. Because in topology, if you, I hope you can still hear me, if you do an interval crossed with an interval, this outside is not exactly the same as this other outside, right? There's a homotopy in between them across this square. And so this is like a quintessential homotopy space. So this is a quintessential path, and this is a quintessential homotopy. Whereas in categories, this is not a quintessential two-dimensional thing. It's just a commuting square. It's a quintessential commuting square. So all you get if you do this is commuting squares and commuting cubes and so on. So the answer is no, not really. You have to be a bit more subtle about it. I suppose another way of putting it is that this doesn't build up dimensions in topology. It just finds the dimensions that are already there. And we don't have dimensions that are already there in category theory, in categories, one categories. So we can't use this method to build them in. Okay. Could you have a functor category with more than two categories, like C, D, E? Well, or would you need to use products of functor categories to get something like that? So the question is, what do you want that to mean? Because if you have three categories, well, are your functors going like this? Because if they are, then you could have a category whose objects are pairs of functors from C to D and D to E, and then the morphisms, I suppose, could be pairs of natural transformations. And the thing is, that functor category is just this functor category crossed with that functor category. And so I suppose the answer is yes, you can, but I personally wouldn't write it like that because I'm not sure what that means. The other thing you could do is you could think about functors from C cross D to E, but then I wouldn't write it like that either. But those are some things that you can do. If you take the dual of a functor category, are the arrows of the functor objects reversed? Now I'm going to need to try and be a bit psychic here because I don't really know what a functor object is. But I think I know what you mean, maybe, because there is typically quite a lot of confusion about duals of functor categories. So if you take a functor category like that, then the objects are functors from C to D, and the morphisms are natural transformations. So a morphism F to G is a natural transformation from F to G. So if I take the dual of that, remember the objects do not change. So the objects are now functors, are still functors C to D, right? And a morphism from F to G is now a natural transformation going the other way. So the functors themselves don't change direction because the objects don't change when you're taking a functor category. Now, this is really something that's happening inside cat, right? And inside cat, you can also take the opposite, the dual of the category of categories, in which case the functors will flip direction. And so what's happening here is that this is a two-dimensional duality, whereas functors are a one-dimensional duality. And I believe that comes back in the last chapter, because there are two types of dual that you can take of a two category, where you reverse the one cells or you reverse the two cells. There's another type where you reverse both, but that's combining both types of dual. So I hope that clears up a little bit. Another question says, what exactly is a shape category? Well, it's true, I don't think I really defined it anywhere, but it's more of an interpretation. It's not a technical definition, because every time we've made a quintessential category like this, then we can find diagrams of this shape inside any other category by making a functor to this category. And so a diagram of shape of any given shape in here is a functor from that quintessential category of that shape into here. And so this is what we often refer to as a shape, or maybe I refer to it as a shape category informally. So it's typically something finite and extremely small that has a shape of diagram that we're looking for inside other categories. The next question, am I right in thinking that coherence conditions are about, there's a typo in this question, but I think it means coherence conditions are about the relationship between the abstract and concrete characterizations. Let me see where this question is about. Oh, I think it's from page 337. So I've got two equivalent characterizations of natural isomorphisms, the abstract and the concrete. I'm a bit confused about this question because I feel like it is just the last the paragraph at the top of page 338. This is often the point of having two equivalent characterizations in abstract math. One is concrete, one is abstract, and the key is to know how the two are related. This is often generally referred to as coherence conditions. Okay, I think that deals with that question. 9, is a constant functor a forgetful functor? Excellent question. Let me see where constant functors got mentioned. Right. So the constant functor sends every single thing to the same object. So you can have a constant functor from any category to any other category, and I might call it delta D. And what it does is that everything goes to D. Now, everything for all x in C, x goes to D. So is that a forgetful functor? I would tend not to call that a forgetful functor because you're not really forgetting properties of the objects. You're just collapsing the entire category to a point. Let me just pause for a second. I think what I want to say is that forgetful functor, it's not really a technical definition. It's more of something that we say to capture an idea of something. And it's really if a functor is forgetting some properties of the object in a category. Collapsing the whole thing to a point is not quite the same thing. So there are two questions about, could you please talk about how indiscrete categories and cliques are useful? Well, so an indiscrete category is where it's isomorphic to a point. And so every object is uniquely isomorphic to every other object. And so you get a kind of star type situation where every object is isomorphic, uniquely isomorphic to every other object. And the theory of cliques, I'm missing something, aren't I? Yeah, a lot. Didn't look like a star at all. It's a way of dealing with something that might otherwise be an equivalence. So this is an equivalence relation. Everything is equivalent to everything else. And if you have an equivalence relation expressed via things being isomorphic to each other, then instead of quotienting out by those isomorphisms, which is kind of ugly, you can take the whole clique of them because they're all isomorphic. So maybe then there's another load of uniquely isomorphic objects over here that has a slightly different shape because there's a different number of them. And then you can take and make a new category of cliques so that the cliques can then deal with they still retain the information about the isomorphisms, rather than when you quotient out by equivalence relation, you just really pretend that all the objects are equal when they're not. If you do it by cliques, then you keep the isomorphisms saying that they're isomorphisms. If you want to look some stuff up about this, they're really good for, well, I like them anyway, for proving coherence for monoidal categories or I've used them in some of my recent research, and I think they're very elegant. And because one thing that often happens if you try and quotient out by an equivalence relation is that because you've collapsed everything to a point, it can be harder to work out what the morphisms should be between those new points. Whereas with cliques, you just kind of keep all the morphisms, and you have these isomorphisms mediating between which morphisms count as the same morphism. That's kind of what it is. So that instead of whenever you make an equivalence, oh wow, that's really loud something. If you quotient out by an equivalence relation, that's a very violent and kind of ugly act abstractly. Whereas like this, you're not literally quotienting out by them, you're just finding a way to say that they're the same, but maintain the information about how they're not the same. Okay, good. I think I'm going to take a break right there. Right, I have had some chocolate. Here we go. Next question. Page 329. Regarding morphisms fx to gy, is this an equality? So maybe I'll switch to sharing the screen that's got the book on it. Okay, so this question appears to be about this, where we're talking about these morphisms. There are two paths around this square from fx to gy. And the question is this an equality? Well, at the moment, it's not an equality. Here, it's a putative equality. That is something that could be an equality. And a potential, maybe it's not putative, it's potential in this case. And the definition of a natural transformation is that we ask for those things to be equal. And that is the naturality condition. Would we want an equality in this case? Yes, that's the whole definition of the naturality, which is here. Is it the case that morphisms can be equal and objects cannot? No, objects can be equal because everything can be equal to itself. But it's not categorical to ask objects to be equal. However, morphisms are the top dimension of a category, and so there is nothing they can do except be equal or not equal. And so it's not ugly to ask for morphisms to be equal, but it's kind of ugly to ask for objects to be equal. Okay, next question, page 330. In the last section of 22.2, would you mind saying more about what you mean by real content? The last sentence of section 22.1. Here we are. There's a certain feeling we can develop that when some transformation feels natural in abstract mathematics, it's a sign that there is a natural transformation at work somewhere, and specifically that the naturality will express the real content. Yeah, it's hard to say what real content means. What it means is, what is the whole point of why we're doing this? What is the whole heart of what it is we're trying to uncover? What is the interesting concept that we are trying to isolate here? Because in abstract mathematics, we're not just randomly wandering around abstracting things. We're trying to do something. We're trying to focus. We're trying to home in on particular behaviors that are pertinent in some way. We don't just randomly abstract this and randomly abstract that, or at least I don't think we should. I don't think that's the point of abstract mathematics. The point is to find pertinent structures or find pertinent behaviors, and that's the real content. That's what I think is the real content. Okay, great question. Okay, page 331, last sentence of the second paragraph of 22.3. What does the shape of alpha mean? Well, it's this shape, the shape of the shape that it makes on the page, the shape. So more abstractly, you can think of it as literally the shape you see on the page, but more abstractly, it is what the boundaries are. I mean, that's what a shape is, right? What's a shape in any language? It's what format the boundaries take. And here, it's that it's got a source functor and a target functor going between the same categories. It's called globular because it's like a globe shape. It's globe shaped as opposed to square shaped. So this is why I put this here. This one is not globular. This one is globular. Why is it called globular rather than globy? Globar. I mean, globy sounds silly. Globar doesn't make any sense, so it has turned out to be called globular. Page 334, in the last sentence of definition 22.6, the idea is that this functor collapses the whole thing to a single point. Yes, that's an object. Page 334 at the bottom, the blackboard, oh yes, I think I addressed this already. Do 0 and 1 need to be terminal and initial objects? Well, look at them. They really are terminal and initial, aren't they? So 0 is the initial object in this category and 1 is the terminal object in this category. So it doesn't matter what we label them, they will still be terminal initial. Page 337. Oh, yes. Could you name which commutativity is being used for each equal sign in the diagram? Okay, so as we move across here, we're starting with these two components equaling the identity. So this proof is a proof about, it looks like a proof about isomorphisms, natural transformations with inverses. What we're trying to do is suppose that each component has an inverse, then we claim that those inverses form a natural transformation, right? So part of the hypothesis is that each beta x is an inverse for alpha x, which means that when you compose them, you get the identity. So that's what this equal sign is. Because we're moving from alpha x composed with beta x to the identity. So the next one is that we're going from this outside of the diagram, this top right-hand part of the diagram, to the bottom left-hand part. And if you look at that, that's just the identity followed by f of f equals f of f followed by the identity. So that's just the definition of identity. Then here, we're going from this identity curved thing to alpha y composed with beta y. And that is, again, part of the hypothesis saying that beta y is an inverse for alpha y. And then we are going to this left-hand, this zigzag left-hand square here. Good heavens, is there part of a diagram missing here? Let me pause. It's all right, I panicked. We're trying to show that the right-hand square commutes. So we don't need to go all the way because we started at that right-hand square. Okay, so here, what we're doing is we're moving from this left hand and the bottom part to this sort of zigzag thing. And so we've moved across this left-hand square, and that's the naturality of alpha. Okay, so that is all of those. Page 342 to 343, last paragraph. Discrete and indiscrete categories have opposite universal properties analogous to discrete and indiscrete spaces, which can be made formal by adjunctions. Can you give the adjunctions? Okay, so we're not doing adjunctions in this book, so I'll just do this briefly. I should switch back to the whiteboard. If you don't know what adjunctions are, don't worry about it. I've mentioned them a couple of times before because people asked questions about them. But there is an adjunction that I honestly remember as going like this: C, D, O, I. And this is for discrete, that's for indiscrete, that's for objects, and that's for connected components. So this is an adjunction dealing with functors between categories and sets. So given any category, you can forget all the way down to its objects. So that's the object functor, and that is left adjoint to the indiscrete category functor. So if you start with any set, you can freely generate an indiscrete category on it. So you take those objects and then you put in a unique isomorphism between any pair of objects. The other thing you can do is generate a discrete category from it, and that's the left adjoint to the object functor. So the discrete category on a set is the one where you just put identities in. So it's kind of the opposite extreme. At one extreme, you make everything uniquely isomorphic, and the other extreme, you just give everything an identity. And then there's a further left adjoint to that, which is the connected component functor. So you can take any category and go down to its set of connected components, which is a little difficult to define because connected components, you can have morphisms pointing in different directions, and that will still count as a connected component. So you might not be able to you can't say that it's all the objects where there's a string of there's a morphism from here to here, because there is not a morphism from here to here because it changes direction in the middle. But a category does break up into connected components. If everything is connected with everything else, then there'll just be one connected component. So in that case, you would get the terminal set. So that's the connected component functor. So there is this string of adjunctions. And so what happens here is that if you try to forget from a category down to a set of objects, a small category, then that forgetful functor has a left adjoint, which is the discrete category functor, and a right adjoint, which is the indiscrete category functor. So that is a sense in which discrete categories and indiscrete categories are dual to each other, because left and right adjoints are dual to each other. Okay, if you didn't understand any of that, don't worry about it, because that, well, you worry about anything you like. But if you didn't understand it, please don't feel like you were supposed to understand it, because we haven't done adjunctions. Okay. Page 346. Okay, I better go back to the book. Someone asks, under definition 22.13, could you expand on what you mean by boundary? Yes. So whenever we're composing things, there is some boundary in between the two things that we're composing, which is where we're sort of sticking them together. And so here, the boundary is the point. Whereas if we do it another way, then the boundary is a line. So let me go back to the whiteboard. So if we have just an ordinary morphism, its boundaries are the endpoints. Those are considered to be the boundaries. If we have a two-dimensional thing, it's got different dimensions of boundary. It's got the zero-dimensional boundaries and it's got the one-dimensional boundaries, right? The two cell in between them is the thing that's going between those boundaries. And so we can stick these together along the zero-dimensional edge part, it's like an edge, or along the one-dimensional edge. So if we went up a dimension, then this two cell would become a boundary of a three-dimensional thing, and then we could stick the three-dimensional things together either along their zero-dimensional boundary, the one-dimensional edge, or the flat two-dimensional outside part. Okay, so the next questions are about composing natural transformations. I think I'm going to take another break. Okay, here we go with the last few questions. Someone says, I'm still feeling a little unsure about how functors can compose with natural transformations and how these compositions result in natural transformations. If I compose an identity functor with an identity natural transformation, how does the resulting natural transformation relate to the functor? Okay, good question. So let me show you how to think through, a way to think through this situation. Let me attempt to use the same notation as in the book, A, B, C. Okay. So if we have categories A, B, and C, and we've got functors F to G, a natural transformation F to G, and then a functor here, H. Take a look at the outside of that diagram, right? What's at the very beginning of this diagram is the very outside. We've got the outside categories A and C. The very top functor, which is, let me draw that again because that wasn't very good. The very top functor is HF. And the very bottom functor, oh, there goes the whiteboard again. Okay, pause, how dull, pause, recording. Okay, let me resume where I was. Here's the, oops, something's landing on me. Let's get rid of that and draw that again. Someone's going past with some loud music. I hope you can't hear it too loudly. Right, what's at the, so what's at the very top of that diagram was H composed with F, and what's at the very bottom of that diagram is H composed with G. And that's because we already know that those functors are composable, right? The F and H are composable and G and H are composable. And so the idea is to feel like in total, what this diagram is giving us is a functor from HF to HG. And so let's investigate what that, what it looks like this diagram should give us is a natural transformation from HF to FG. So that's the desire that we feel or could feel. And we might call it H alpha, because what we're going to do is we're going to do the identity on H in this part and alpha on that part. And so now we can play around with it and see what is given to us by this information, right? So what would a natural transformation from HF to HG have to look like? It would have to have, for every A in A, a component from HF of A to H of G of A. Now, what morphism do we have that looks like that? Well, look, over here, we've got for every A in A, we have a component alpha A that goes from F of A to G of A. And so if we just apply the functor F to this whole thing, that functor H to this whole thing, we get H alpha of A. And so then if we once we've checked that this is natural, this is a natural transformation that has just popped out from this information. And so that is how we can compose a functor with a natural transformation. Now, the last part of this question was, if I compose an identity functor with an identity natural transformation, what happens? Well, let's investigate. If I have an identity natural transformation, so for example, I could have the identity on F. Why did I write that as a D? That's very strange of me. This is a V. Okay, so I have a functor F, and I have the identity natural transformation from F to F. And now the question is asking me to compose that with an identity functor, which is going to go from B to B. So now, what is the outside of this diagram? Well, now it goes from A to B, and the top functor is F composed with the identity, so that's just F. And the bottom one is also F composed with the identity, which is just F. And because everything is the identity now, I hope you are feeling that this ought to be the identity. So now that we've felt that it ought to be the identity, let's see if it really is, because what the formula tells us to do is apply this functor to that component. And that component is the identity, because the identity natural transformation has all its components being the identity. So this is indeed the identity as well. So that's what happens when you compose that identity with that identity. Okay. Page 349, could you more slowly walk us through how you got to the diagram at the top of the page? Yes. So page 349 is the diagram about interchange. Okay, so what we've got here, the scenario is we've got A, B, and C, and we've got 4 natural transformations. So we've got alpha and beta over here, and we've got P, Q, and R, gamma, and delta over there. And there are 2 different ways of composing these. We can either do the horizontal composition first and then the vertical, or the vertical composition first and then the horizontal. But the key is to remember how horizontal composition is defined. And so if we do it by whiskering like this, then what that's going to tell us is that if we do horizontal composition first, then we're going to do alpha whiskered with P, and then we're going to do G whiskered with gamma. So that is what the next diagram down is trying to indicate, that we do if we're doing horizontal first, then we're doing alpha whiskered with P, and then we're doing gamma whiskered with G, and then we're doing beta whiskered with Q, and then we're doing delta whiskered with H. Okay, so now if we write out what all of those components are, let's try to remain calm. This is always going to be for every object of A. So the first thing is we're going to do P whiskered with alpha. And so this is going to start at P F of A, and it's going to go to P G of A. And that is P of alpha of A. Right, now the next stage is we keep G where it is and we go down gamma. So this is going to take us to Q of G of A. And because we've gone down gamma, but we've gone down gamma at G of A, right? And now the next thing we do is we go down beta whiskered with Q. So this is going to take us to Q of, right, beta goes from G to H, so that's Q of H of A. And this is Q of the component beta at A. And then I didn't draw that diagonal in the way that I should have done. And then finally, we go along delta whiskered with H. So that takes us to R H of A, and the component is beta at H of A. Let me look to see whether I did it the same way as I did in the book. And the answer is yes, there are two ways of doing it, because you could whisker the other way around first. So then the other way of composing this is that we do the vertical composition first. So the other way of doing it is that we do alpha. No, that's not a good way of drawing it. We do alpha and beta together, and we whisker them with P, followed by gamma and delta together, and we whisker them with H. Now, how do we do alpha and beta whiskered with P? Well, we do alpha whiskered with P and we do beta whiskered with P. And so the first thing we do is alpha whiskered with P, which is what we've already got here. But now we're going to do immediately beta whiskered with P, which means we do P of beta at A, which takes us to P of H of A. And now we do gamma and delta whiskered with H. So the first thing we do is gamma at H of A. And then we do, this is not a delta, this is not a beta, that should be a delta. And so that's how we get the diagram. Okay. Then someone else says, could you explain further what you mean by that one follows by definition in the middle of the page? So in the middle of that page, I'm talking about, whoops, this whiskering thing. And so it's about the fact that if you do something like that, so let's call this gamma delta with F stuck on the beginning. Oh, you know, someone said, how does the diagram in the middle of the page follow from functoriality? So let's do that one first. So the first one says we've got alpha and P, and we've got beta and P, and we're trying to show that it equals alpha beta composed with P. Okay, so what does this one do? This one says, let's write some things in. This is F, G, and H. So this says we're going to do P of the component of alpha A. So this takes us from P F of A to P G of A by doing, whoops, P of the component of alpha at A. And then after that, we do P of the component of beta at A. So that's that one. Whereas the right-hand side says we do alpha compose with beta, and then we do P on it, right? So alpha compose with beta, what this one says is that we do it all at once. So we do the component of alpha compose with beta, right? But the component of alpha compose with beta at A, it's defined to be the component of beta composed with the component of alpha. So what we're doing here is P of that. And we're asking whether this is the same as that. And it is because of the functoriality of P. So that's why it's about functoriality. Whereas if we do it the other way around, then we're doing gamma, and delta with F at the beginning. And we're asking if that is equal to gamma composed with delta with F at the beginning. So if we look at the first one, then what we're doing, so this is called P, Q, and R. If we look at the first one, we're going from PF of A to QF of A to RF of A. And the first one is gamma whiskered with F. So that is the component of gamma at F of A. And this one is the component of delta at F of A. Right? Whereas this side is we're going straight from PF of A to RF of A. And we're doing it by doing the component of gamma delta composed with gamma at F of A. But by definition, this is the thing that's the definition. The component of delta composed with gamma at F of A is by definition the component of delta at F of A composed with the component of gamma at F of A. And so it's really by definition of composition of natural transformations that is true. Okay, good. And finally, page 350, just to make sure I'm tracking with this, could step 2 also be written as apply the interchange law? So let me go back to the book. So here it is. Step 1 is the definition of horizontal composition. Step 2 is whiskering the other way around with the middle two fish. So this proof is a proof of the interchange law. So step 2 better not be an application of the interchange law, right? Because then it would be a cyclic proof. And the point is that it's not the full interchange law. It's just the whiskering the other way around. And the whiskering the other way around thing comes from basic definitions about how we compose, how we do whiskering. And so it's more that general interchange is built up from principles about whiskering. It's not. So step 2 is a specific case of interchange, but you shouldn't refer to it as interchange because we haven't proved interchange yet. We're trying to prove it. Okay, good. That's all the questions. Wonderful. Some final praise. Thanks for your commitment. The videos are really helpful. Thank you. Thank you for helping us through this challenging material. I'm glad you're still here. Let me go back to the full thing without the share. Thank you for your dedication and patience. Thank you all. Thanks very much. Thanks for pausing our questions and responding to them. It feels very validating. I'm really glad about that. So grateful for this book club and all who make it the wonderful thing that it is. Oh, wonderful. Well, that's including you and the Topos people. Thanks for all your help, Eugenia, Smiley. Well, thank you all for still being here. We're so close to the end. The questions about the innate lemma are going to come in soon. I'm very much hoping no one has asked me to just prove it, but I'm excited to see what there is. And then we'll be on to the last chapter, which is absolutely amazing. Well done for still being here. Thank you to everyone at the Topos Institute for running this, and thank you for your wonderful questions. Bye.